Men will be taught that beneath and behind all the outward beauty of our lowlands, our uplands and our highlands, there lies an inner history which, when revealed, will give beauty a fuller significance and an added charm. Archibald Geekie, Landscape and Literature, 1905. Our planet is such a special place, enlivened by an incredible ecological richness of fauna and flora. But the accelerating loss of natural habitat and species mean that biodiversity is on everyone's lips. And yet, underpinning biodiversity is its hidden silent partner, geodiversity. The basis of every ecosystem are the non-living elements of nature: rocks, minerals and soils, and landforms and topography, mountains, gorges, rivers and lakes. This geodiversity has its own intrinsic value, worthy of protection. And it has an essential role for the human planet. It provides the building stones for our towns and cities. And it provides the material for our energy resources, including renewable energy. So as well as underpinning biodiversity, geodiversity underpins human diversity. It's the bedrock of our national and cultural identity. The foundations of Mother Earth, our common home.
Welcome, everyone. Thank you so much for joining us for our event, Celebrating Geodiversity, the Critical Foundation for Diverse Ecosystems on a Changing Planet. I have to say this is the second time in my career that I have followed in Stuart, and it is daunting. My name is Beth McClarty-Halfkenny, and I'm a geoscience educator, so the topic of this evening is dear to my heart. By virtue of our studies and work, Earth scientists have a privileged opportunity to think about deep time and the importance of place. And so I would like to take a moment to acknowledge the connection to the land that Indigenous people have had since time immemorial, and the tremendous value Indigenous traditional knowledge and practice brings to the work of storytelling about the Earth. It's my pleasure to be your MC this evening, as well as the moderator for our panel discussion, which will follow our keynote speaker. Please join me in welcoming Christina Tessier, President and CEO of Ingenium, and Carleton University Board of Governors Committee member.
There's a headshot. Welcome, everyone, and thank you so much for attending this event this evening. Celebrating Geodiversity, the critical foundation for diverse ecosystems on a changing planet. Well, I know, that's notes from Beth, just a second. I should be more organized. I'm going to start over. Welcome, and thank you so much for being here. I'm going to formally begin the evening with a land acknowledgement. Today we are joining you from the city of Ottawa, which is built on unceded Algonquin-Anishinaabe territory. During this evening's talks, we will be discussing the many ways that our Earth is made of interwoven strings, the great diversity of our planet, the rocks, the soil, the atmosphere, and the cycles of water and other nutrients give life to the innumerable plants, creatures, and societies that call our planet home. Reflecting on these connections can help us to be better stewards for this diversity and build a better world for all. With this in mind, I would like to acknowledge the ancestral caregivers of this land and acknowledge the treaty lands and the ancestral and unceded territory of all the Inuit, Métis, and First Nations people. On behalf of Ingenium, I am very pleased to welcome you tonight to the Canada Science and Technology Museum for our first live Curiosity on Stage event in over 2 years. Acting as a bridge between science, technology, and society at large, our goal is to explore the role that innovation and exploration plays in shaping our shared future. We hope to foster open conversations about the state of science and technology, the benefits that it could have to our society, and also some of the challenges it still faces. Subject matter experts are key to these discussions today, and we are fortunate to be welcoming 6 experts to speak to us about the past, present, and future of our planet. I would like to extend a special thanks to the Department of Earth Sciences and the Carleton Faculty of Science co-hosting this special evening that celebrates the physical diversity of our planet, a topic which is integral as our society adapts to a changing Earth. It is my pleasure to introduce the Dean of the Faculty of Science at Carleton University, Maria De Rosa.
Thanks so much, Christina. Thanks for opening up this amazing space for us to have this important conversation. As Christina mentioned, this is a very special evening for the Faculty of Science at Carleton and the Department of Earth Sciences, as we come together to commemorate and celebrate the inaugural UNESCO International Geodiversity Day. Geodiversity refers to the abiotic, or non-living parts of nature, the rocks, the fossils, soils, and landforms under our feet. These features are an integral part of our living ecosystems and environments, including human societies, providing nutrients, other resources, food, clean potable water, building materials, and the critical minerals needed to create our clean energy technologies. Through our outreach programs, we are working toward informing and educating the next generation of earth scientists who will be the solutionaries that will help us to move towards sustainable societies. Beth McClarty-Hafkenny, the Curator and Outreach Coordinator for Carleton's Department of Earth Sciences and President of the Canadian Federation of Earth Sciences, has assembled a dynamic roster of panelists for this evening's discussion, including Stephen J. Cook, Director of the Institute of Environmental and Interdisciplinary Science at Carleton University, Jan Peter, Research Scientist, Economic Geologist with the Geological Survey of Canada, Peter T. Dang, Entomologist and President of Biodiversity Conservancy International and Conservator of the Pinny Sand Dunes, and Tessa Diorio, Source Water Inspector with the Risk Management Office at the City of Ottawa and Secretary of the International Association of Hydrogeologists, the Canadian National Committee. We look forward to their contributions to what we're certain is going to be a really lively and thought-provoking discussion, taking place after the keynote address by Dr. Claudia Schroeder-Adams, Professor Emeritus, Department of Earth Sciences at Carleton University, who has graciously returned back to Ottawa and Carleton from her home on Salt Spring Island to join us here this evening in commemoration of this inaugural UNESCO Geodiversity event. Dr. Schroeder-Adams has spent her research career on understanding how ecosystems and landscapes have changed through geological time. Her area of focus is on the Cretaceous time period, so 145 to 66 million years ago, where our planet was vastly different than it is today. The Cretaceous greenhouse climate and its geological drivers had a profound influence on polar flora and fauna, making the Arctic a fascinating subject. Her specialty is micropaleontology, a field that addresses the smallest and fundamental organisms in the marine food chain. As a professor of earth sciences at Carleton University from 1992 to 2020, Dr. Schroeder-Adams traveled extensively with her students across Canada, to Canada's Arctic, to the Antarctic, France, Germany, New Zealand, to bring all this experiential learning to her students. For Dr. Schroeder-Adams, research is not only limited to the academic world. To make discoveries accessible to everyone, she produced a documentary called Arctic Greenhouse. It premiered at the Canadian Museum of Nature and was made widely available in Nunavut. She received the Mercator Fellowship from the German Research Foundation, honoring her long-standing scientific collaboration with the University of Frankfurt in her home country. And now she is sharing her work once again with us. So without further ado, please join me in welcoming Dr. Schroeder-Adams for her talk entitled Remarkable Earth and Ecosystem Changes in the Canadian Arctic Through Deep Time. Welcome.
Thanks. Thank you, Maria, for this introduction. What one all does in life. So I like it. One moment here. I can, I guess, walk around, which is good. So I like to take you to the Arctic. The Canadian Arctic is an absolute special place. And it was the great highlight in my career that I got a chance really to work there. And so that's why it's one reason I have a lot of enthusiasm for this work. So that is one reason why I take you there. You see there behind the glacier our little tents. This is where we live when we go in those kind of areas. But before I take you north, I like to first take you south. And just to demonstrate that biodiversity and geodiversity is always very much linked. We know as people, we talk a lot about biodiversity, and as geologists, we of course know that biodiversity is based on geodiversity. And that's why I'm so delighted that Beth had this idea of this whole forum, and she approached me, a year ago, and she had this idea that we need really to bring this forward in honor of this UNESCO Geodiversity Day. So think about a reef. This island here is Heron Island, and I spent some time there. It is at the southern end of the Great Barrier Reef in Australia. And you can see this little island here, and this is the whole reef flat. And it is just all organisms. We know that reefs have a great biodiversity. And you see it here, the reef flat, and a close-up over here. Lots of different organisms. They all live at the photic zone because they are depending on algae in symbiosis with some other animals, and algae, of course, are plants which need to photosynthesize. So now, if you put geological processes, big-scale geological processes, to a reef like this, such as uplift, lifting the whole thing out of the water, the reef will die. Submergence, if it is submerged too quickly so that the corals cannot keep growing, into the photic zone, the reef will die as well. Or we are sending a whole lot of sediment onto the reef due to fluvial input, the reef will die as well. So geology and geological processes are related to biodiversity. So now we travel to the Arctic. We are going into the very highest areas here, way up into the Arctic islands, the Queen Elizabeth Islands. And you see here that we have ice caps. We have, of course, the last Greenland ice cap, but we have also some ice caps on these islands along along Baffin Bay here as well. Now, these are NASA images, and we can see that winter ice, 2021, winter ice is covering the entire Arctic Ocean. It's a polar view of the Arctic Ocean. If we go to the summer ice, we can see that we have a much reduced ice cover in the same year, 2021. And this yellow line shows you the average minimum ice cover from 81 to 2010. And we can see that it was much more extensive compared to now. So the summer ice in the Arctic is melting fast. When we go 20,000 years back, we're going into the last glacial period, and of course we had a gigantic ice cover. You know, we had this ice cover of North America all the way down here on the Great Lakes. So the ice cover extended south of the Great Lakes. And ice has given us the landscape we know all so well, with the millions of lakes. You know, as the ice retreated, we have, you know, the erosive power of ice. We have ponds, we have lakes, we have rivers, we have topography through all the moraines, you know, which are associated with the ice. So this large ice sheet has given us the landscape you know today. You know, we all enjoy by going into these lakes and swim. So it had to come a long way from here to this, what we see nowadays. You know, all this has melted, was several kilometers thick. All this has melted, and now we have these last ice refuges, which is of course associated with those animals which need the ice to survive. And you know, we know, you know, of these. And as this ice melts, we are getting changes. Just to show you the variety of Arctic landscapes, here I choose the island of Bylot Island. And one project we had here, and you know, we have really nice mountainous regions here, of course not much vegetation, polar region, just some very shallow grasses here. We have glaciers in the back. We have thermokarst lakes, which are the result of melting permafrost regions, getting all these little ponds here, and meltwater streams, you know, which are fed from melting glaciers. And we have high cliffs, which often seabird colonies are living at, you know, and of course surrounded, all these islands, by the marine environment, which I actually studied in my life, more the marine environments than the terrestrial environments. And where's Bylot Island? Just here, north of Baffin Island. The glaciers. We have glaciers. We see very large land glaciers here. They're meeting up here, coming from two directions. And over here, this is Bylot Island, this is Ellesmere Island, and then we have also sea ice. And of course, all these ice areas are melting. And when we melt sea ice, that has not a great influence on the sea level. On, you know, that sea level is not really rising when we melt sea ice because we are not adding to it. But if we melt land ice, like these glaciers, and eventually all sending that meltwater into the oceans, that brings sea level up. And that is one of the very large problems, of course, in our society nowadays. Just to give you an idea, if we really melt all ice on Earth, of course, Antarctica has a long way to go, but if we do that, sea level is 70 meters higher than nowadays. So you travel to Nova Scotia and march along the beach there, and then sea level 70 meters higher. That floods a lot of land. Okay? So we had, of course, times like that. There is life up in the Arctic. There's beautiful life. We have here the examples of the flora, and these small plants, they are often very small, they have a lifestyle where they explode as soon the warmth is coming, and then they go and hibernate for a long, long time in darkness and in the cold. So they never grow very large, they hover to the ground, and also to withstand the very cold winds up there. But certainly the Arctic flora is of great beauty. And then we have animals. We have here, you know, the mammals. We have here the the musk ox on Axel Heiberg Island, we have an Arctic wolf, we have an Arctic hare, and they are very nice camouflaged in white areas, you know, with their fur. We have the Arctic tern, the absolute champion in migration routes, flying 45,000 kilometers every year from pole to pole and back. So it's a remarkable bird and always tries to peck your head when you come too close to the nest, you know. And then, of course, everybody knows these very enigmatic polar bears, and I put them in there, and you can see these are all my pictures. This is not my picture here. I have never encountered, in all my work up north, a polar bear. I'm kind of glad for it, you know, because I always feared them, that they would come in camp, although seeing one from a plane or so is nice, but not in my camp. And that's what I studied. We cannot forget the importance of the microscopic life. The microscopic life is the base of the food chain. And we have various types here. We have the so-called protists, which are the microscopic algae, and we have diatoms here, which have siliceous tests, and dinoflagellates, which are organic walled. And then we have the protozoa, so on the animal side, microscopic, siliceous tests again, the radiolarians, and then the calcareous foraminifera. And all these live in the modern Arctic, in, you know, the Arctic Ocean and its neighboring marine settings. The importance, of course, of this is they form the bottom of the food chain. If you take those out, or if they are not healthy and they are not multiplying, you have an effect on the entire food chain. And we had times in geological time where that exactly happened. So, climate. We talk today all the time about climate. You know, climate change. People are so worried about climate change. And really, we should talk about the climate warming, because climate change has always been with our planet. The climate goes warm and cold and warm and cold, and we see this very clearly on this graph. So here's our geological time scale here, and you know, part of it. And you can see in this curve, here's the temperature. From 11 degrees to 28 degrees as an average global temperature. And we can see that we have high times and low times, and we are distinguishing ice house conditions when it's cold. We are distinguishing greenhouse conditions at different levels of it, and when it's getting further up. And we have also hothouse conditions, and then it's getting pretty hot. So we can see that some of these changes were quite gradual. We are looking here at 550 million years. So they were quite gradual. When they're gradual, biota have a chance to adapt. You know, they can either migrate away, or they have a chance maybe to survive. If it's abrupt, animals or plants have no chance to adapt, and they become extinct. And we had phases like this as well. Look at this one, where we suddenly drop into the ice house. That's at the end of the Cretaceous, when we lost the dinosaurs. And we know, of course, it was a meteorite impact. And suddenly we get a very short spike in total coldness, because the sun was covered by debris in the atmosphere. And we know that at this time we lost a large amount of organisms, which we call a mass extinction. So when we go now to our time here, our last end here, we again have a very fast change, and that is what we are responsible for as humans. And it's going up into warmer and warmer climates, and we are causing a mass extinction. So all these were natural causes, and in this case, it is one species giving us the mass extinction. So why we have the different causes of climate change? You know, like just very briefly, it's a very complex subject, of course, but very briefly, a few causes. The sun, this is reminding me, this picture here of the sun. The sun radiation and its intensity has changed through geological time. And also the path of the Earth around the sun is also changing, so the distance between Earth and sun is changing, giving us climate variations. Then, of course, this is a reminder of the greenhouse effect, where we get these greenhouse gases, and with that, you know, like keeping the heat, you know, close to Earth and not having it radiating back into space. And the last one here is the tectonic pictures, how our globe really has changed. You know, like plate tectonics gives us very different continental placements, and you know, like on Earth, and we compare here, for example, the Cretaceous and the present day. And you can see in the Cretaceous, we have one open ocean in the equatorial region. And that water, the equatorial currents, just go around the globe and just get heated up further and further and further. You compare this with nowadays, there's a land barrier there. There's the Panama Canal, but you know, there is a land barrier there with Central America, and with that we are creating this conveyor belt of water masses, and we are getting warm water going to the north or to the south, and they're cooling there, and they're coming back to the equator, and with that everything is in a better equilibrium. So very important plate tectonic picture at geological time, influencing, you know, our climate. And just to remind us of Earth processes, this is, here we are flying over Axel Heiberg Island, and we are seeing this black band here. This is a basalt sequence. So these are large magmatic plumes which are coming up into, you know, and get into the crust, into the Earth's crust, and then later on they are, you know, exhumed by erosion, and these tell us that there is hot magma coming up. And those kind of stages we had throughout Earth's history from time to time, where massive amount of magma was, you know, being pushed up, and often it's associated also with volcanism, and that in turn gives us, of course, increased greenhouse gases. So we need to look at all that, and at the end, that all influences life on Earth. So I'd like to take you to 3 different localities and show you how the polar region was actually looking at the time. And we go here first, we go back in time slowly, and we're going here first to about 4 million years back. Here's our climate curve, a little bit zoomed in, and we have here really hot house conditions, then we get into cool house, and eventually into ice house. So this locality is about 4 million years back, and we are looking before it drops way down into ice house. Interesting here is, these are the models, the predictions for the future, you know, with our CO2 contents, what might actually happen if we do something about it or not. So we're going Ellesmere Island, and we're looking at this locality. Just an amazing place, Strathcona Sound on Ellesmere Island. And we had our tents built up down here because the plane can land here. And then our working space is really way up here. So every morning we had to come up, and since I was part of the team in my age, we called it the cripple run. you know, so that I have to go all the way around here, and not straight up. That was too hard for me, you know. So we are working up here, and this is a project of my friend Natalia Rybczynski, who is with the Museum of the Canadian Museum of Nature, and it is really her research, and you know, I had the privilege one year to accompany her, and it was truly a wonderful introduction to the high Arctic. Natalia, you might hear me here. So that's the area way up there where we want to look at. And what do we see there? We see large packages of peat. Now that tells us, of course, that there had to be a lot of vegetation there. You know, like otherwise you're not, when you compact it, you don't get meters of peat. Nowadays, you're not producing peat in the Arctic. You know, so it had to be warmer, it had to be vegetated. And what we also found was, or what they found before we went there, or I went there was a pile of sticks. And those sticks had beaver gnawings on it. And so there was actually an ancient either beaver dam or a feeding pile of beavers. And there were also fossils found, you know, which actually this little small beaver here, and other fossils, bear fossils, little horses, little ducks or ducks here. And so this person, this artist, reconstructed this whole area in this manner. And a beautiful landscape which would not be found on Ellesmere nowadays. The range of beavers nowadays are like this, and nothing up there. Okay? So a different climate altogether. And how do we reconstruct this? We are looking at you know, the whole section. We are looking at every little detail. We are finding charcoal pieces. So then we had an artist, Stefan Thompson, who made this beautiful cartoon here for us, where we have a floodplain with a river, then we are forming vegetation, then we are getting a pond with a little beaver pile there, and eventually we get a forest fire. You know, so with all this detective work, we can then reconstruct what that part of the Arctic was like about 4 million years back. So then we go to Axel Heiberg Island, another area where I think it's a remarkable place. I take you to an area where I have never made it to, but it is such a special place that we have to include it. But unfortunately, I never made it there. So, we are going to Geodetic Hills. So this is Axel Heiberg here, here's Ellesmere, and so this is the Geodetic Hills. And we are looking now, here's our climate curve back, we are looking at this particular area here about 45 million years back, just after we had hothouse conditions. The Eocene and this whole hot area on our globe was a remarkable phase where around the globe we have immense biodiversity, where really evolution made a leap, a total leap to radiate, and it's due to these warm climates. And this was also true in the Arctic. So Axel Heiberg Island, here we are finding a forest of dawn redwood trees, metasequoias. And that's, you see the stumps here. They're very well preserved, all these big stumps. Then we see whole leaf litter, like beds of leaf litter. We see cones, we see wood, where it is so well preserved you could put a match to it and burn it in your stove. You know, so this is basically a polar fossil wetland forest, which first got buried by sediment, and eventually in the cold time, then when the Arctic became very cold, it these were unearthed, but the coldness preserved these wood pieces and prevented the rotting of it. So we are looking at temperatures there, of average temperatures of 18 degrees. So an absolute remarkable site, which, in my eyes, needs to be protected. It needs to be protected. It is a testament of, this polar region under these very warm conditions. And when we look at quickly how the Earth was like, here is modern polar view again. We have large openings to the Atlantic Ocean, and here through the Bering Strait to the Pacific. In the Eocene, it was not quite like that. The northern area here, the Arctic Ocean, was much more enclosed. We had small passages, but it was much more enclosed, and it could warm up. And this is a reconstruction by someone at the American Museum of Natural History, and we have these tapir-like creatures and these very big trees, these swampy forests. An amazing site, absolutely needs to be protected. So now we're going to Glacier Fjord. This is something where I have worked a lot. And here again, there's our camp, and you wake up and then you look at this, so it's not the worst job to have. But strong winds, so 110 blew over. But so this is a very special area. Let's first look at the Cretaceous, very important. Here is our Cretaceous, 145 million years to 66 million years. And what do we have? In this, I draw your attention to the orange box here. And the Cretaceous is marked by various parameters. First of all, greenhouse climate. Nice warm, nice climate. The production rate of oceanic crust, so tectonic activity, very high, very, very high. Connected with constant volcanism. We see that as ash beds in our sediments, one after the other. Carbon dioxide content higher than nowadays, where we still have cold up there, so quite a bit higher, but not as high as we have way back in the Cambrian and Ordovician. But certainly elevated. The temperature, at times hothouse. At times hothouse, but certainly greenhouse. And the sea level, due to all this production rate of oceanic crust, super high. 200 meters higher than we have nowadays. Now imagine the Earth with sea level 200 meters higher. All coastal big cities deeply underwater. So this is what geology can do. A total change. And as we look at North America, throughout the Cretaceous, we can see that, the white is land and the gray is water. And throughout this time, from old to young, we had sometimes these enclosed basins, and sometimes sea level was so high that we formed a wide open seaway connecting the polar sea with the warm Tethyan Sea down here. And of course, organisms migrated from the south in here and migrated from the north in here, forming a very interesting environment. And so the sea level changes, driven by various factors, have such an overprint on the globe and on biodiversity. So I take you to this area because it is plain amazing. Here is the 80 million years. This picture looks, oh, there's a little pile of rock. No, it is 7 photographs put together. And so we are looking at the depositional history over 80 million years. That's amazing to have without a single vegetation covering it. That's why we go to the polar regions, because we can reconstruct what we like to reconstruct. And there are several arrows here, and these are the changes in sedimentary packages. You know, we go here, for example, from these very yellow sands to these darker shales. And that means the environment has changed. So we start with the oldest, the way it was deposited. Of course, the oldest first, and then we get younger. So we start with the oldest, and it looks like this, where we have very much an interaction between fine and coarse. Fine and coarse. And sometimes with large beds, and sometimes with very narrow beds. And that we interpret as a delta. And a delta here, we see it's, of course, a river bringing a lot of sediment into the ocean, you know, and it's having all kinds of channels. And as these channels switch, where you have sand in the channels, because lots of energy of the flow, and you have mud on the mud banks beside it, and as these channels switch through time, you get these packages of different sediment. And so this is our large Isaacson delta. And to remind you what it was looking at, or what a delta is, I put here the modern Mackenzie delta. And it's an amazing labyrinth of arms, water arms, and ponds, and so on. And, you know, some people go in there from the south and they want to go fishing, because it's very rich in wildlife there, and they want to go fishing, and they get hopelessly lost every time, you know. And then the Inuit have to come and rescue these people, you know. So that happens often. And here is a picture. I had the pleasure of flying over it, and you can just see here how, you know, all these ponds are forming this wonderful delta. If we go back to the Isaacson, these are images from there, and we have big petrified trees, we have branches, and we have a lot of coalified plant debris, which the river is bringing into the water. So that's our delta. As we move onwards, we are going into, you know, in time, now we are at 112 million years, we have this big package here of shale. And here's, for example, a bentonite, which means an ancient ashfall. So there was a volcanic eruption and gives us this ashfall here. It's full of marine shells, you know, and it is really a marine shelf setting. So sea level rose, covered the delta with marine shelf settings, which are deeper than the delta in terms of water depths. Then we go now into the Hassel Formation. The Hassel Formation about 110 million years back, and we're looking at a beach. Eventually, this is not yet here, but eventually when we come to the top, we have these sandstones, and we have a beach environment, and full of trace makers. Like, look at all this sediment is churned through by organisms which are organic. They have an organic body, so they don't leave any fossil, body fossil, but they leave the traces of their activities. And with that, we know that there was life. And then we have these little dots here. And these are vertical burrows where the animal, when it's on the beach, where we get constant wave action, just hides in the sediment. And the other day, I was in Tufido. Here is your modern analog, you know, like a nice beach. And here are these little holes where these animals just hide, you know, when it dries up, and later on, when the water comes again, then they start feeding. So always nice to compare modern analogs with the ancient depositional settings. So then we're getting eventually into this very black unit here. And that's still under investigation what that might be. It is together with the volcanic or the basalt flows. We see here these basalt packages. And so, and we lose all marine organisms. So are we looking at a pond or a lake? has this eruption to do anything with this. So we are still working on that. So that is possibly a freshwater setting. And then eventually we get into deep marine, very fine-grained sediments. We get nice ammonites here. You know, they like to be also further offshore. And to look at this, we are at very high temperatures here. Here's the temperature curve, increased CO2, and we get these areas which are organic rich shale, and sometimes they reflect anoxic bottom waters due to a stratified water column. So in that Kengak formation, which is there at the upper, geologically younger area, we again have primary producers. Very important. So we have dinoflagellates, we have these wonderful diatoms here, and they help us as biostratigraphic markers. And we also have siliceous radiolarians. So organic void, siliceous diatoms, in siliceous radiolarians. But we have no calcareous organisms, like plankton, calcareous plankton. So what is the explanation for that? Are they dissolved afterwards, or were they never there? Can we make a point for ocean acidification in that very warm polar sea? We talk about ocean acidification nowadays a lot. As we warm the oceans, that we have signs for ocean acidification. And that would take out one group of plankton right at the bottom of the food chain. We also have larger animals in the Cretaceous. We have here this image here by James Havens. We had a lot of dinosaurs or found in Alaska. So most of the Arctic dinosaur discoveries are from Alaska. And we have these bones here, and there are crocodilian-like animals way up on Axel Heiberg Island. That tells you that it must have been a really balmy climate in Axel Heiberg Island, because reptiles in general are not way up here. This is the distribution of the reptiles. They like it warm. So the Arctic at that time was warm. So just to summarize this section and why it is so special. So we're going from, a delta environment to a shelf, to a beach, to a lake, and to a deep shelf. And each single one, over 80 million years, each single environment has its own biodiversity. And as geological forces change that sedimentary basin, these assemblages change with it. So the interwoven, relationship between biodiversity and geodiversity is very, very strong. So just we do go full circle, and we are coming back here to the modern Arctic, just for a moment. I don't work on the modern Arctic. I always worked in the past. But here we see the Stacy ice field. And we see, of course, a nice meltwater channel there. But there's one other thing we see, and that's very important. This ice is very much covered by sediment, by darkish sediment. And what that means is that when the sun radiation is coming down, it absorbs far more the energy and the warmth than when it's just nice and white, clean ice. So with that, it changes, with that sediment on top, it changes the albedo effect. And with that, it accelerates the warming of the Arctic. So you see it in this picture very clearly. And we have other signs for warming. We have methane bubbles, like the permafrost, these gases are frozen in the permafrost. As the permafrost melts, they're bubbling up. It is an enormous process right now in the Arctic, and no one can predict what it might contribute to the global warming, because this process really cannot be stopped, at least not for a long, long time. So it's a very critical point. Then, of course, we see plain erosion here, this big glacier. We have side moraines, we have the big end moraine. Of course, the glacier was way down here, and it just retreats and sends a lot of meltwater down into the ocean, into Glacier Fjord, into the ocean, and contributes to sea level rise. And here we see major permafrost melt, causing huge slumps. And that is something which influences the infrastructure in the north greatly and has a huge effect on the northern people. The Arctic amplification. It's very complex, but just to remind you again, we have here sea level rise, we have here the temperature curve, the global temperature curve, increasing here, becoming warmer, but in the Arctic, it is much faster. It just jumps higher up. And that is that we have the Arctic, what we call Arctic amplification. And one reason here is shown in this picture, where we see the dynamics of sea ice and the areas where we have melted sea ice. These are darker. These are darker than plain white sea ice. The more it melts, the more we get these darker areas absorbing the sun's radiation, contributing to continued warming. And we have that on the glaciers itself with the sediment, and we also have it on the marine sections of the Arctic. So this brings me back to the very important question of primary productivity. Me, as a micro-fossil person, here I'm contrasting the Arctic food web today and the Arctic food web 80 million years ago. Now, what's the difference? It shows very clearly. Nowadays, we have ice. And so much life is actually associated with ice. We have snow algae, we have under ice fauna. And of course, we have here the polar bear, which has to hunt on ice. And we have in the Cretaceous, we had times where the Arctic or the polar sea was ice-free, and we had vegetation. However, the limited sunlight was the same, because it also had a polar position then already. So all organisms have to cope with long darkness in the winter. Just they have to do here, they did there as well. But we do not have that ice there. So in all this work we do, we ask ourselves, can we actually bring the Arctic, with the way we go about the production of CO2, will we actually get at some point to this particular scenario? You know the CO2 ppms, like we are now, I think, at 415 ppm. And this was the latest measurements. In the Arctic, in the Cretaceous, we were at about 1,000. Researchers who researched this particular problem suggested if we keep going without any changes and we use as much as we are using now, we would reach eventually 1,500 ppm. Then we have reached and surpassed Cretaceous conditions. So I leave you with that question, you know, what we do about that. And I'd just like to have a bit of an acknowledgement. The Arctic is an expensive place to work, so you need for sure some research funding. And I have this very wonderful collaboration with my colleague here and friend Jens Herle from Frankfurt University and David Harwood from the University of Nebraska in Lincoln, Nebraska. So we are continuing with the work despite my retirement. And I have worked with amazing Northerners. Here is Jomi Inugu and Keenan Lindell. Keenan was my cameraman, which allowed us to do the documentary Arctic Greenhouse. And you know, I have learned so much from these people about their culture, about their hardship of living in the North, and about their whole outlook and their knowledge of the land. So when one works there, one always should hire a person from the North. They need the work, and they are the best additions to any kind of team. And then, of course, I like to acknowledge my work with students, which I always enjoyed so very much. That's really something I miss, where I'm now retired. You know, the youngsters around me, really bad. And this is my last slide. So thank you to UNESCO for declaring the Geodiversity Day. Very much, you know, it was needed. And I want to thank Beth, I want to thank that you brought it to Ottawa and to Canada, and I think this was the best idea. And then I would like to thank the people of Nunavut who allowed me to work on their land. Those years where I was working there, and hopefully I can go one more time, it enriched my life to a degree which I cannot describe. It just was wonderful. And here, just to bring back to biodiversity, we are looking at this very disturbed area, you know, like lots of erosion and so on. What do we have here in purple? Arctic fireweed. You know, fireweed always coming as the first colonizers when you burn down an area in the Yukon or wherever, you know. And here, these first colonizers, Arctic fireweed. Thank you very much.
Thank you.
Oh, sorry, dropped something. Thanks, Claudia, so much for your wonderful talk and for describing your field investigations in the Arctic and bringing us these fabulous images. I'm sure many of us will never get a chance to go there, so that was really, really wonderful. We have a few minutes if anybody has a question for Claudia about her talk. I'm grabbing this technology because we have some people on the Zoom audience who have some questions. There was a question about whether the Anthropocene epoch has been ratified. I'm not sure if it has yet. I think it's soon.
I think it has been ratified. I'm not working in those modern times, but maybe some of geologists here, I think it has been ratified, I think. It is on geological charts now.
Yeah.
So I think it has been ratified. I would think so.
I think there's a question about where we should, whenever we define a new epoch, we have to find the place on Earth where you can see it and point to it and put your finger on it. So I think there's still some discussion about what will actually define the Anthropocene.
It is, of course, related to the tremendous warming. You know, we are basically creating a whole new climate on this planet with great influence, again, on life on the planet. You know, this very fast warming, which really will move to another mass extinction. And that's kind of the tragedy of it all.
Wonderful. Thank you so much.
Yeah.
Thank you, Claudia. So at this point, I'd like to ask our panelists to come to the stage and join us so that they can lend their expertise to a discussion about how geodiversity affects our everyday lives. So we're going to move to the panel discussion. So please join me on the stage. While they make their way to the stage, I'd like to remind everyone participating online that you can drop your questions into the Q&A located at the bottom of your screen. And for those in our audience, to raise your hand or to address the panel if you want to speak from your seat, and we'll bring you a microphone, or make your way to one of the 2 floor stand mics at the front. And while everybody's getting settled, I'd like to pull some ideas from UNESCO's Director General Audrey Azoulay, who published an open letter about Geodiversity Day this week, and hoping that this can help us to frame our discussion. She encourages us to examine the close relationship between geodiversity, biodiversity, culture, and heritage, and the complex relationships between living and non-living worlds. Geodiversity has been called the silent partner of biodiversity, as we saw in the opening video, providing critical supports to Earth's many diverse ecosystems, including human societies. Ms. Azoulay notes that geodiversity underpins food production, water management, energy production. I'd like to add that municipal planning and responsible decision-making relies on a sound understanding of local geodiversity and processes that form our regional landscapes. And now, if everyone is settled, please join me in welcoming our panelists. So furthest from me, on your right, is Dr. Stephen Cook. He's a biologist, Canada Research Professor, and the Director of the Institute of Environmental and Interdisciplinary Science at Carleton University. His work spans the natural and social sciences with a focus on developing solutions to problems facing aquatic ecosystems. He's also founding director of the Canadian Centre for Evidence-Based Conservation, and he will be inducted into the Royal Society of Canada in November as a fellow. Dr. Cook. Beside Dr. Cook is Tessa Diorio. She's a hydrogeologist at the City of Ottawa in the Infrastructure and Water Services Department. She's the city's designated risk management official under Ontario's Clean Water Act and focuses on the protection of source water for municipal residential drinking water supplies. Tessa also supports the review of new development applications in Ottawa related to private servicing and manages various groundwater-related projects to support informed resource management decisions, groundwater protection, and long-term sustainable development. Tessa also serves on the board of directors as secretary for the International Association of Hydrogeologists, Canadian National Chapter. Welcome, Tessa. Next to Tessa, moving closer to me, Dr. Peter Dang is a retired taxonomist with Natural Resources Canada and an entomologist. He specializes in Microlepidoptera, specifically leaf rollers, budworms, and bud moths, mosquitoes, and other biting flies, and the ladybird beetles. I commend you, sir. He is president and founder of Biodiversity Conservancy International and publisher of BCI's scientific periodical called Biodiversity. Dr. Dang is the project director of the restoration and conservation of the Pinnie Sand Dunes, a rare and unique prehistoric inland sand dune habitat in Canada's capital, working to support the biodiversity within this geology-specific ecosystem. Welcome, Dr. Dang. And then sitting next to him and in the very middle, Dr. Jan Peter is a research scientist at the Geological Survey of Canada in Ottawa. He specializes in the field of economic geology, which is the study of mineral deposits, together with exploration methods and techniques used to find them. Currently, he's focused on researching the distribution and control on so-called critical minerals within base metal deposits. These elements are needed for the green and digital economy and the transition to clean energy. welcome to Jan. Sorry, I have to move to my chair. So I'd like to start with asking you a question, a general question, and then we'll open it up to the audience. Can you tell me, panelists, how your work relates to geodiversity? And I thought we could start with Dr. Dang, because I think it's easiest to see the connection in his work between a sand dune and the plants and animals that like to live upon it. So maybe you could expand on your work for us.
Yeah. Actually, I just started working on the biological aspect of the sand dune system. But actually, we just opened up a lost geodiversity site in Ottawa, completely lost. Based on the area photo taken in 1925, this geological site is very big. It's really extended from the Pins Complex all the way down to York River and railway. You know, it spans across about 4 square kilometers. So that's a very large area. Okay. And at that time, the site is still very pristine. You can see the dune and the distribution of the biodiversity of the dune very clearly. Like, you know, the dune have its 2 sides. One side is the very windy side and very sunny, hot. And the very special and unique biodiversity of sand dune occur. And the distribution of plants in the leeward side, you know, the side away from the wind, actually that you can see the vegetation from Canada. That's a native vegetation road there. So the distribution is very clear. Now, when we open up the sand dune, one earth science scientist, Dr. Alan Donaldson, he came to me and said, you know, you guys open up not a biodiversity site, but this is a geodiversity site, important site in Ottawa. And I realized that this is really important. So at that time, we started working on the sand dune in association with the geodiversity and biodiversity of the site. Now you can see the interaction between the biodiversity and on the sand dune and the sand dune itself. The sand dune is the iconically very important geodiversity site, and the biodiversity of the sand dune is very unique. They cannot survive outside of the sand dune, outside of this geodiversity site. The structure of the site is very clear. You see the sand dune made up of sand. The sand grain very small and round, and that's really suitable for certain organisms that live in the sand dune. You know, especially one ghost tiger beetles live in the sand dune. Very special tiger beetles, very common in the sand dune, but very rare elsewhere. You know why? Because the sand dune has the structure of the sand. The sand grain is really important. And the depth of the sand is also important for this creature. So that the combination of all kind of geological attribute to this site really accommodate for a certain group of biodiversity. So in short, you know, biodiversity of sand dune is very unique in the Ottawa area. They can only found at the Pini sand dune. This is a very special geodiversity site. And we appreciate that. And now the public also learn to know about the site. And you see, you know, the attraction of to the public. Thousands of visitors came to the dune every year to see the site. And we always appreciate the university, school children, and the children from the student from grade 1 all the way to university level came to the dune to study about the site. So now I think, you know, I try to talk about the conservation of biodiversity. Actually, conservation should include geoconservation, that is sand dune, and biodiversity, bioconservation as well.
Thank you. Thanks very much. For the rest of the panel, can you tell me how your work relates to geodiversity? Maybe I'll pick on Tessa next.
Thank you.
You're
Glad
welcome.
I'm next up. I guess understanding geodiversity is really a cornerstone to sustainable development planning, and that's sort of the key. I'm a hydrogeologist, and my passion is clean drinking water. Sorry, if I'm talking too loud or too...
Just don't touch
my mic. Sorry, I'm Italian, I move my hands a lot. So my passion is drinking water. I'm the risk management official at the city. I also help out with development planning. So when we look across the city of Ottawa, we don't see a lot of relief like in those beautiful mountain pictures you showed, but there's a lot of action happening underground. We have a very complex geology in terms of the bedrock geology. We have faults in the area like the Gloucester Fault where you have water quantity is very different on one side and the water quality which is reflected by the rocks that it moves through. So that water quality, water quantity, that's very different. So we have a complex bedrock geology. We also have a very complex overburden geology. Claudia had shown a lot of pictures about sort of the features from the glacial features. We have old remnant seawater from the post-glacial lake, the Champlain Sea in the area, and we have areas where we have the old Champlain seawater is actually trapped under there, and so if you drill a well, you're going to get seawater. So understanding the distribution of the geology, understanding water quality in aquifers and how much water you can get out of the aquifers, that's really a cornerstone to being able to plan development. So I work in mostly in the rural area. Both the municipal wells, we might want to plan for municipal supply wells. So one of the features that we have in Eastern Ontario, these big esker features. So the Vars-Winchester eskers runs from Vars, which actually their municipal supply is in the esker, all the way up to Winchester in Stormont, Dundas, and Glengarry. And it's a prolific aquifer, and you can actually find villages all along there because that's where they kind of found the water. So that's one piece would be the water, water quantity, water quality. Another piece I'd like to highlight, which isn't my wheelhouse, but also very important for development planning, would be geohazards. We have to understand what are, like, I guess we also have the Leda clay in the area, which is a big landslide risk here. And we have to know where these hazards are in order to protect people and to protect property. So there is a very big link between, I guess, understanding geodiversity and sustainable sort of long-term development planning at a municipal level.
Thank you. Thanks very much. Stephen, can you tell us about your work and how it relates to geodiversity?
Sure. I'm going to take you back to high school. So one of my earliest forms of summer employment, I was hired by the Grand River Conservation Authority as a summer fisheries technician. And it was my first week. I was super excited. You know, I previously worked at Arby's, and this was a real big move, right? I was getting into science. And I should say right off the bat, I'm absolutely addicted to fish. I love fish and fishing and fishery science. So that's me. I'm the fish head. So arrive, and I just expected we would be handling fish, you know, assessing fish, measuring fish every day from, you know, dawn till dusk. That's what work was going to be about. And they handed me a ruler and a flow meter and some sieves and sent me out. And it was all about the habitat. We spent the first month, I didn't see a fish, but I saw a lot of rocks. I spent time learning about and understanding the systems that we were working in, mostly small streams. And then it was later on in the summer that we went out and eventually started catching fish and started to see those associations between the habitat features that we'd measured and where the animals were actually distributed in space and time. A little bit later, I ended up going to university and took an ecology sort of oriented program, and in 1996, I took my first fisheries science class, and we had to choose a group project, and I selected the intersection of fish and geology. And so I've been training for this night for 25 years. And that linkage has just become more and more apparent to me in a variety of ways. And so we oftentimes talk about how habitat is the foundation for healthy and productive fish populations and aquatic ecosystems, and I firmly believe that. And we talk about habitat. Yes, there are, you know, the down trees that fall in, and there's the vegetation, the macrophytes that grow up from the bottom, and so on. But it's really the geology that underpins all of that. So if you think about, and this extends back, just even the species that we have here today are very much driven by the Wisconsin glaciation. So 11,000 years ago, we had ice sheets that covered this area, and as they retreated, they created the water, and carved out those water bodies that we see on the landscape today. And it's really evident, as somebody that has some research boats in our lab, how what we see on the surface extends below to what the fish see. And I know that because oftentimes students will take a shortcut around an elongated island and take the bottom off of a motor. And you know, I think about that as a landscape that continues underwater. And that's what the fish see and what the fish experience as well. And so we're at a point where, unfortunately, we're in a freshwater biodiversity crisis. Globally, freshwater fish not just fish, freshwater biota down about 80% according to WWF, the WWF Living Planet Index. And so we're investing a lot of effort in restoration. And when we talk about restoration, there's a number of things we can do. We can certainly, you know, bring animals into captive facilities and try and, you know, propagate them there and throw them back into the wild, but that doesn't work so well. What we need to do is be focusing more on restoration. We're also, not to overshadow the day of geodiversity, but we're also in the UN decade of ecosystem restoration. And when I think about what we need to do for my favorite fish or freshwater ecosystems more broadly, it's the habitat side of the equation. We need to really focus on improving and enhancing, restoring those habitats. And that means working closely with experts from earth sciences, geomorphologists, ice experts that can help us design structures that are not wiped out by the first ice flows that come down the river. So as somebody that spends a lot of time with a mask and snorkel on underwater, I can attest to that relationship between the geodiversity that I see underwater and the biotic diversity which I love to study. So, thanks.
Thank you. And last but not least, Jan, can you tell us about your work?
Sure. I'm an economic geologist, so it has nothing to do with the economy. Well, I guess it's basically metallic, or not only metallic, there's also non-metallic minerals that we extract from Earth, basically mining to use for all these different purposes that we need them. So recently there's been a push throughout the world to focus on what's called critical minerals, those so-called minerals that we need for the new green economy and the digital economy. And as part of that initiative, the Canadian government, I'm with the Geological Survey of Canada, which is an arm of the Natural Resources Canada. And so we, together with other partner countries, are basically making an inventory. This is the end game, or the long-term or mid-term goal, is to make an inventory of what critical mineral resources we have. And it's not that easy because a lot of these occur in very small amounts. Trapped in minerals, we used to, when they would be processed and smelted or ball milled and refined, would be thrown away into tailings ponds or thrown the baby out with the bathwater. So now we're backtracking, and we're trying to take an inventory of what we have and where they would be concentrated and what would be potentially economic. So as part of that initiative, to do a blanket survey, and this is ultimately throughout Canada, we had to classify the deposits that we have into different types. So before we could do that properly and ascribe, like postage stamp collecting, put them into different silos, we had to make an inventory, or we had to make a classification system, which we did together with the United States Geological Survey and also the Australian equivalent called Geoscience Australia. And so to do that, we created this really diverse classification system, and when Beth invited me to take part in this, I didn't really I had to investigate and think about this a lot. And the first thing I'll say is we the answer that I can provide just goes directly to that classification system. So if you look at the whole gamut of the mineral deposit types that we have on the planet that we know about, and then sometimes there are new ones that we are investigating, and they're quite rare now. We mostly know what we're dealing with. They encompass rocks that are, there's a whole bunch of influences on the mineral deposits. Mineral deposits are mines. And if you talk to my neighbors or anybody, they think, well, you just dig a hole here and there's a mine, right? It's very complicated. They're very rare, and there's a very particular set of conditions that must occur for a mineral deposit to form. Particularly one that's big enough that's economic to be mined. And so they occur in a whole host of what's called tectonic settings. Claudia showed a good snapshots in time of plates at different periods, like current and also back in the Cretaceous. And of course, this happened all throughout time. And there are periods in Earth's history where there was prolific volcanism and plate movement, and lo and behold, a lot of mineral deposits formed. Those ones linked to volcanic rocks, magmatic rocks, which are, there's a whole host of tectonic environments where plates were sinking and then subducting and causing abduction, causing volcanic arcs to happen. And so magmatism and volcanism. And then there are also places where certain mineral deposit types require sedimentary basins. So exactly the opposite, quiet conditions, where you have salt flats accumulating, and then these get juxtaposed to other environments where there's hot water activity in basins, and minerals flow through these basin sequences, these thick sedimentary basins like Claudia showed, and extract leach metals due to from hot solutions, and then these are deposited at certain periods in certain specific sites. So mineral deposits form in basically everything from magmatic rocks, sedimentary rocks, igneous rocks, and in a whole host of tectonic environments. And so it's really the interplay of what I do is the unraveling of the complexities that can arise that lead to mineral deposits formation, and we use mineral deposits forming, and we use that information to back calculate or to make models and derive what's called mineral potential mapping. So we can make maps based on what we know, and we make maps and use those to guide explorationists to take us to areas that they can further focus on. So the diverse tectonic and geologic environments really lead to the whole gamut of mineral deposits that we have. And without this geodiversity, we would not have the plethora of minerals that we do have access to, particularly in Canada, because we have a wide variety of these different diverse geologic and tectonic settings. Some countries are blessed with more so than others, and Canada is one of those that is really well blessed with diverse geodiversity.
Thank you. So I would love to open the questions up to the floor. If anybody has a question, to come down to the microphone. If not, I have a couple more of my own. So following on your discussion about your work and minerals and mineral resources in Canada, can you tell me how Canada is positioned to supply those kind of minerals that we need for, say, battery innovations? So
I'll just set a little backdrop before I get into the Canada side of it. I mentioned that certain countries and certain nations are more well set up. They have the perfect storm of the perfect geological settings in which these mineral deposits, these freaks of nature, I guess they are really, they are freaks of nature. You don't dig a hole anywhere just to find something. And so certain nations are blessed with more critical minerals. There's certain, we call them minerals, they're metals, but mostly, but then some of them are minerals like graphite and potash. So everybody's heard probably, it's been in the news of late, China, for example, controls 70% of the world's rare earth elements, which are used for all sorts of high-tech purposes, but particularly to make magnets for electric motors, for electric vehicles, and for wind turbines. And so not only do they control the 70%, have 70% of the production of them, the mines, they also control the value chains, that the processing, the manufacturing, all that goes with it, or goes beyond that. So, and for example, everybody's heard of cobalt, one of the minerals that is elements that's necessary for electronic batteries for electronic vehicles. So, because of DRC, the Democratic Republic of Congo, controls 70% of the world's cobalt production. So, based on that, I'll cut to the chase and be quick. There's a big realization amongst countries in the West, well, all around the world, that we need to pay much closer attention to these, because these countries that these critical minerals are situated in could be geopolitical controls that are not geological, that can control our access to them. Excuse me. So Canada is very well positioned in a number of critical minerals. We're the #1 producer of potash in the world. #2 is uranium. We're the #2 producer of uranium. We're high in aluminum, not from the sourcing of the raw material, but from the production side of it. And there's a whole bunch of things that we're well known and famous for: copper, zinc, nickel production, for example. And lately, when I say lately, over the last few decades, Canada has slipped in its production. So we're no longer, we used to be like #3 and #4 in a lot of these. And we're now down around 6 or 7 or 8 and lower. So basically, we have a lot of work to do to backfill and get our position up, and also, more importantly, to increase the value chain. So not only just extract it out of the ground, but to do other things with it, process it, smelt it, refine it, and manufacture with it.
Thank you. We have a question?
That's my question. Is this on? Good. Hi, Claudia. How are you? So I have a question for Claudia. I have 2 questions, if that's okay. So, Claudia, you showed a graph of the potential warming in the Arctic, but with different predictions. But even with sort of the best case scenario, the Arctic is going to warm considerably. I mean, do you have a comment in terms of sort of what the Arctic will look like sort of in a few years? And sort of both in terms of that, and then I also wonder sort of about the preservation of these sites that you're at. How is it going to affect sort of, the ability to look back in the past?
Well, the preservation of these sites is extremely important, and it's interesting. Despite the absolute remoteness of this area, there are coal companies interested in actually, taking coal out of these areas where, this vegetated material attests to much warmer climates. And there is quite a conflict going on between actually paleontologists and geologists who think that they are so valuable for the reconstruction of past Arctic climates, and business interests of coal companies. So that is an ongoing conflict. In terms of the change in the Arctic, I think it's very grim, because we don't halt this anymore. And I mentioned, for example, the release of gases with the permafrost thaw. This is set in motion, and really no one predicts when this, if we can halt it even and bring this to a stop. And what one predicts right now is that with the Arctic ice in the Arctic Ocean, that we might have lost, that it is completely open during the summer months by 2050. So this is not far away. And of course, this has all kinds of follow-ups in terms of the business world, because ships want to go through there. It just cuts off so much the journey between the Atlantic and the Pacific if you can go through the Arctic Ocean. And, the northern people are very concerned about that, because with ship traffic comes pollution. And that's their hunting grounds. So there's all kinds of conflict and very desperate predictions, really, for the future.
I suppose the loss of ice, the ice as well, could potentially open up possibility for like mining and other resource extraction as well.
Absolutely. I mean, as soon there is access by ship to certain localities, then companies want to go in there and take resources which Jan just talked about, out of there. And us paleontologists, we like to protect the paleontological significant areas. And then there's a whole other problem with these northern mines. You need to also employ northerners. Yeah. And I mean, that's a different story altogether, but it's very important. These people need jobs up there. So if something is built, those people need to be hired. So that's, and I learned this also well by having my field partners from Nunavut. I had such wonderful conversations, but also heartbreaking conversations with them, about this and the lack of employment there. And so if a mine is built and all people are brought in from the south, that doesn't help these people at all, Yeah.
Great, thank you.
Yeah.
So I have a question for Tessa too, if I can have my second question. Is that okay?
Sure.
So Tessa, good to see you as well. Obviously with changing climate, what is the City of Ottawa doing to potentially plan for that, like in terms of water resources or clean water or flooding or that kind of thing?
Oh, that's a very large question. The city has a whole they have a part of a department that works specifically on climate change initiatives, and the city has a large climate initiative. I can talk from, as the risk management official, I can talk from the source protection point of view. So I help, I guess, look at the municipal drinking water supplies, and we have done studies on the municipal drinking water supplies to determine if there are going to be issues with water quantity in the future and water quality in the future. So we have done water budget work for those municipal supplies, showing that the main body of water that supplies to the city is the Ottawa River, and we're not really at risk of losing water for the population. So the Ottawa River supplies to over 90%, so about 900,000 people take water from the city of Ottawa, use that water. And then for the municipal supply wells, we have one well that's a little bit shallower, which is being deepened right now, so we don't see the risk to the climate change for our municipal systems. It will be different once we get to the private wells, and people might start to see some changes, and especially people with a shallow well, and we do see that on a regular basis. So we have a low water response team that works through the conservation authorities, run low water response programs, and so we do see annually people with shallow wells that might have wells that go dry every year, just because they're water table wells. So we do see that. In terms of the city's initiatives, like I said, there's a whole department working on initiatives right now, and there's I can follow up with you. I know I don't know if I can say more about that, but it is top of the city's mind, and there are many initiatives right now.
So what is it about that causes the wells to go dry? Is it mainly just changes in precipitation?
Yes, so it's sort of an annual drought cycle that comes. So and it's not every year. So it's the precipitation. So when we get low water, and we do monitor. So I should say before I worked at the city, I worked at South Nation Conservation. So when I say we monitor, when I worked at the Conservation Authority, I did assist with that program and monitoring. But there's a low water response system in place. So the Conservation Authorities both look at water levels in the streams, and they look at water levels in wells, and when they get to a critical level, they'll declare low water, and they'll have some actions that they'll take, or they'll recommend people take, like with lawn watering and things like that. But yes, when people's wells go dry, it's usually the shallow dug wells. There are people, so when I worked at the Conservation Authority, I did the intake of calls for people whose wells go dry, and it's a very common practice in Eastern Ontario for people who have a shallow well to have their wells filled by a water hauler. So I've had, yes, I know, this is, really? Yes, it's very common, and I would call, like when we went into low waters, it was one of the things I would do, would call the water haulers and say, are you filling wells? And yes, and the wells are in a porous material, so the water table drops, and your pump is no longer pulling water out because it's gone down, and they got the water haulers, and I've talked to people who say, I got the water hauler in every 2 weeks, and they fill my well with water, and by 2 weeks the water is out again. So this is a common practice. But just, sorry, to go back to the question, it is typically the dug wells that go dry that are more affected. And that's one of the things we'll advise people is if their well is going dry quite often, that they should probably have a deeper well or drilled. In some areas in the city, sorry, I can keep talking about this for a while. In some areas of the city, people's only option is to have these shallow dug wells. As you're aware, we do have some remnant salt water trapped below the Champlain sea clays. So we do tend to get, like in Alfred Plantagenet, eastern part of the city of Ottawa, where if you drill a deeper well, you're into more of that saline water, so they can't really use it. So then they have these dug wells, so people are stuck with sort of these dug wells that continually go dry every drought season. And that's part of the city's responsibility now. So anytime a new lot is created, it's the city's responsibility to make sure that that lot can be safely serviced. So we very rarely allow the creation of a new lot if it's going to be on a dug well, because we do see these issues that come up all the time where the well is going to go dry. You're going to have water quantity issues. And for these shallow dug wells too, you typically have water quality issues. So you're tying the dog out next door. If you're in a sandy unit, the dog pees, and the next day that dog pee is going to be in your well. So we typically don't like to have these shallow dug wells, but they are out there because they're existing lots of record, and people need to get water for their house. So yeah, sorry, that was a roundabout way of saying yes. It's typically the dug wells that go dry, and it's the city's responsibility and responsible development planning to make sure that new developments can be sustainably, I guess, serviced in the long term with safe wells that will not go dry into the future and that can produce good long-term water quality.
Appreciate your passion for water.
So.
Thank you.
Do you have another question?
Please. My question is mainly for Dr. Cook, but I think Ms. Del-Oreo could also touch on it. Given the expected growth of the city of Ottawa, both in terms of suburban sprawl and population, how are we supposed to be able to balance reintroducing habitats into freshwater areas that you study?
Yeah, so every time a road goes in, every time a house goes in, it matters for fish and other aquatic organisms, because when a drop of water hits, impermeable substrates, asphalt, for example, it's going to run off. And so we get a couple things happening. So we get really weird hydrographs where when it rains, all of a sudden we get these massive flood events. And then we also get less infiltration. So and then that starts to affect groundwater inputs into systems as well. We see wetlands starting to dry up and so on. So it is a real balancing game, and certainly a lot of local stewardship and government organizations organizations, conservation authorities in particular, very active in trying to figure out what we call offsetting strategies. So for example, if this neighborhood's going to go in and is going to lead to the loss of or alteration, damage to some of these small surface streams, for example, what can be done? So we're doing a fair amount of work in the Jock River system where there's a fair amount of development. So you can think out towards Barrhaven Way. And we're studying right now some sites that have been restored. And oftentimes with restoration, we build it. We throw money at it, we build it, and we walk away, but we're not actually sure whether it worked in the end. So we're going back, working with the City of Ottawa at some of these stormwater facilities and with the Rideau Valley Conservation Authority to actually assess whether or not they work. And so there's a lot of great work being done on the ground, across the globe by practitioners, but we're not doing a good job of assessing what works and what doesn't and sharing. And so we don't share our failures for sure. They end up in in back of somebody's mind or in a file drawer, but we're also not sharing the successes either. And so that's something that we need to do a better job of. So it's incremental, and it's a multi-scalar governance challenge as well, because you've got federal legislation with respect to the Fisheries Act, you've got provincial legislation, you've got municipal legislation and so on, and all sorts of people at the table all working towards the same end goal of that balance. It's not about no development, it's about how do we develop in a reasonable way. Do I think we can get to a place where we have that balance? Yes. Are we there right now? No.
Thank you.
Do we have any more questions from the floor? There's a microphone on either side. Yes, please.
I did have a question. It's a general question, just for the panel as a whole. Dr. Schroeder-Adams brought up the connection with her research in the Arctic to the local peoples in which that research is being done, and I was wondering if anyone on the panel had any ideas about how to sort of bring in a bigger connection with the earth and environmental sciences to the actual communities that a lot of the research and work most directly affects. Is that something that comes up in anyone's careers and or research, and whether there's a need to change the approach that environmental and earth sciences has in connecting to local communities?
I can give you a little bit of an anecdote from the perspective of the Geological Survey. It's now absolutely de rigueur, mandatory to do engagement with the local communities where the work is being proposed, and we need their buy-in and cooperation and permission to undertake those works. So I don't know, I have the advantage of being at the survey for a number of decades, and it's completely different than it was before. So I don't know whether it's enough, but I do know that there is we have actual groups within the survey whose job is engagement, and to coordinate it and to make sure it happens and that the right people are connected with the scientists that are proposing the work.
I think, if I just may say, it is a very interesting question and I'm glad you brought this up. I think we have a long way to go in incorporating their knowledge. And you think they live day in, day out on this land. And they have a lot of knowledge, which they just have different methods. They have observational knowledge because simply they live there and they work that land. And I believe that we have to bring more respect to these people, that we incorporate their knowledge into our science. And in some scientific fields, it is, for example, if you work with fish, in the north, I mean, these people, they just simply know. You know, they just know. You can totally learn from them when you come as a southerner and come north. And there are still scientific teams. I know the survey has very much the mandate, but I know that there are still scientific teams which try to circumnavigate in hiring someone from a northern community. Because it is, you have to find the funding. Working up north is extremely expensive. You have to find the funding, flying them to this particular locality where you work. You have to come up with a good salary. And so they try to not do that and bring another scientist from the south. And in my eyes, Polar Shelf, who is the absolute hub for all the logistics, they should not send anybody up north and fly anybody to their locality if not a northern person is hired. So I think we have a very long way to go in finding that connection with a lot of respect for what they can actually bring to the table. So we are not there yet, but I'm very glad that you asked this.
If geodiversity of the Earth's crust determines distribution of critical mineral resources, how are leaders, national, international, UNESCO, working to ensure that there can be equitable access to these minerals and metal resources, which are necessary to enable a net zero carbon future for all? Is Canada involved in global dialogue about this? If yes, which department? Does anybody know the answer to this question?
Sort of the geopolitical discussions about well, I know there are alliances and allies and partners that Canada works with, and other countries have their own sets of partners. But I guess the strongest, or the way to what I'm familiar with is that there are allegiances and unions and partnerships formed and forming that are, but there's not, as far as I know, at a global level.
Right. It's a good question, because I think it's going to be coming, because resources will be not as plentiful as we would like them to be. I understand that copper is going to be one of the things that's a problem.
Well, there's a lot of these things we need on the order of, and the International Energy Agency is a report that you can all download if at your will. Just go, it's for free. A lot of these things like cobalt, nickel, copper, rare earths, all are going to be needed. If we are to get to this 2050 net zero target, we're going to need on the order of 10 times to 30 times, so double-digit amounts of these metals and metalloids. So it's going to take a whole bunch more mining. So yes, there's a huge demand and a huge urgency about this all across the world.
Good question. Thanks for that. More questions from the floor? I'm sorry, I can't see anyone. I can just see a shadow.
Is this thing on? Yeah, I guess it is, yeah. Yeah, I was asking about the sand dunes and Pinny's Point sand dunes. And well, my sort of impression of sand dunes is that they can grow very quickly, or they can shrink very quickly depending on the weather and various factors. I mean, are these sand dunes stable, or do you have to make an effort to keep them the same size as they are now?
Well, Pinny sand dune actually very stable now. It's stabilized because, you know, in the 50s and the 60s, they planted 30,000 trees in the area, completely covered the sand dune area. So the sand dune wood trees around and really stabilized, very much stabilized, as compared with the sand dune that we learned from the photograph in 1925. And that time, the dune really dynamic and migrate along with the wind. So now the windy sand dune now is actually became a very fixed landmark. And because of that, and that we have all the sand at the windy sand dune is completely constant. We cannot have any more sand supply from any sand field around the area. So that's all the sand we have. And the biodiversity that live in the sand dune and windy sand dune actually, they depend on the sand. And they really adapt to survive in this sand dune as compared with, you mentioned about the Piney Point. The Piney Point doesn't have a dune. That Piney Point is just near the water. Piney sand dune is an inland sand dune. And it's completely different from the coastal dune. So the diversity and the Piney sand dune has become very, very local and subject to be excavated from the area. The numbers of species like the ghost tiger beetles is subject to excavation. Actually, listed at risk of excavation from Ottawa area. In the past, there are a number of butterfly dune species. There are 2 butterfly dune species from Ottawa region. One is called cornet blue, has been completely excavated from Canada. And the other one is the dusky wing, dusky wing skipper butterflies. Last seen in Ottawa in 2008, before we restored the sand dune. And that species also live on sand dune. Now excavated from Ottawa, but a few area in the south of Ontario, there's a few pockets still remain. In that context, we try to restore or just retrieve or recover that species, that endangered species, back to Ottawa with a planted host plant, trees, shrub, and native plant. Try to bring back that butterfly back to the sand dune of Ottawa.
So another habitat restoration kind of work. That's. Sorry, I wanted to say that if people have never been to the Piney Sand Dunes, you have a great opportunity to see them on Saturday. We have an event called Geoheritage Day, where we have volunteers go to various places across the city where you can see exceptional geology, and they're willing to explain what you're looking at. Mostly they're places you've been before, but you don't actually look below your feet. And one of the places we're hosting with Dr. Dang and other volunteers from the Biodiversity Conservancy is the Piney Sand Dunes. So you'll be able to go see them on Saturday from 10 to 3 and talk with the people that are doing that conservation work.
When we start the restoration, actually, we see the connection between dune biodiversity and the sand dune very, very tight. They got tight connection. When we start restore the site, I said the site nearly completely destroyed in 2010. We started restoration in 2011, and the first thing we have to restore the sand dune, the habitat or the geodiversity site. That is the first thing, the first step. And we have to restore the quality of the habitat. Everything is on non-living component of the site before we start restore the biodiversity. Because the biodiversity totally depends on the substrate, the sand, and the structure of the sand dune and the Piney sand dune. As you said, the sand dune, peony sand dune is very well stabilized because of the trees around it, and that's all the sand that we have now. And biodiversity really shows you something like the ghost tiger beetle. They really occur very abundantly in the peony sand dune, but not elsewhere, because the sand quality, the sand grain that are important. Have a fine sand grain, and also the depth of the dune, not required for this species. So the association between the ghost tiger beetle and the habitat, the geological site, very important.
So we have another question.
Hello. Very interesting, fascinating conversation with biologists, hydrogeologists, economic geologists, university professors looking at deep time. Listening to all this and thinking about the concept of geodiversity, the word is kind of new, but everybody's familiar with biodiversity and the Convention on Biodiversity, and that leads to conservation, discussion, protecting land. Canada is signatory to the Convention on Biodiversity that aims to get 30% of our land put aside through various means so that nature can rebound. So my question for the panelists, thinking about that and the crisis we have in nature and in humanity, climate change and all these things you mentioned earlier, I'm wondering if the concept of geodiversity, how do we apply it to engage with Canadians in the hard choice that we have to make relative to protecting land? There's hard choice to be made relative to minerals. As Jan was saying, they're rare. They might be occurring in these places that are unique from a biodiversity perspective. So how do you see this concept playing out in society going forward? It's kind of new, and we're kind of starting this tonight, and going forward it's going to be an interesting conversation. Thank you.
If I can just weigh in, I think this is going to be one of the balancing acts that we have as a society, to kind of look at all of these competing requirements. We need these specialized elements to be able to move to an energy transition that will help the planet and climate change, but we also need to protect our habitats and environments. And as we've been talking about, those habitats and environments rely on particular kinds of geology and geological processes. So it's going to be a question of society deciding what do we actually need as opposed to maybe what we want. Like, do we need the new iPhone, or can we use the phone we have, right? And do we need things smaller, and do we, how far do we need to go in our electric vehicle with the battery being smaller and smaller? So there's a lot of choices to be made. I think there's a lot of innovation that can happen, and it's kind of a situation where you can be very sad or very excited about what we can potentially innovate to solve some of these problems. But they're quite complex, I think, and interconnected. Steve?
Yeah, I just want to play off that point that we have so many problems in our world today that are super complex, and no one person, no one knowledge domain, no one department can do it all. And so I think one of the themes that I'll certainly take away from tonight is this idea of the needing to work across boundaries and continue to break down the silos that, we're in silos, we're in different departments, but we clearly overlap in many ways. And it's not just about, it's not just about needing the ecologists and the earth science folks together. We need the economists, we need the social scientists, we need those that study human behavior and health and well-being. It's all connected. And so I think the more complex the problem, the more brains and knowledge domains and perspectives and, of course, other ways of knowing. We need all of that. And so as we move forward, I love the concept of geodiversity, and that it again interfaces with biodiversity. And I don't think we should think of them as one and the other. I think, to me, it's how do we bring these together, because one supports the other and they feed back, and that was very evident in your presentation as well. So it's all connected.
Excellent.
And it's education, you know, it's early education to move, you mentioned too, how do we move forward? You know, the education, it has to start in elementary school and then go through the school system all the way to university. In my university years, which was 28 years at Carleton, and Maria, you are you know, the Dean of Science, I always felt that even in the science faculty, we do not work too close, you know, close enough together. And you mentioned we have to even build bridges to the other faculties as well. And I think we have to start very early. And that brings us to something which Bess has devoted her life to, bringing earth sciences as a field into schools. You know, we are teaching all the sciences from physics, biology to chemistry and so on, but we do not always teach earth sciences as a fundamental science field in the early upbringings of a young mind. And I think that is something, this evening, I think totally it has shown that we need this and that your work is not in vain. It is so necessary that we all follow through with that, you know, because knowledge will, you know, make strong minds, and we need to foster that throughout wherever we can educate, I think.
So that we can build those solutionaries that Maria was talking about. Are there any more questions out there?
I have a question here.
Please.
So you've all touched on absolutely wonderful, wonderful elements of geodiversity in the local community and the broader community in Canada. And just to kind of keep this train going for the future of geodiversity, what sort of challenges do you see for the future of kind of advancing geodiversity as a subject, as something that we talk about, you know, every year and things like that?
If I can jump in here again, I've been working to advance the idea of geoheritage for a very long time and trying to put the geological history of the planet in context of the heritage that we usually talk about, which is our own human or cultural heritage, and that it's one bigger story, right? And so I think there's, again, this a tension between trying to protect and illuminate and educate about areas of exceptional geology that help scientists and help other people understand and appreciate Earth and the Earth processes, and having to find copper and having to rebuild a fish habitat, right? So I think it's starting. I mean, having had this day declared is really helpful to get the global mindset around, including the abiotic parts of the Earth as part of nature. I think Indigenous communities have a much more inclusive concept of the Earth and all of its parts being all one community, and certainly not abiotic, which is interesting. So we have, UNESCO has created the Global Geoparks Program, which is sort of a geology education plus economic builder in smaller areas. We have 5 geoparks in Canada right now, and we have 7 that are aspiring, and what they are is an area where there's interesting geology that can be understood and promoted, along with economic things like whitewater rafting companies or museums or you know, art festivals about rocks. And so they create these communities. There's one in that I got a chance to go see before it was designated in Bonavista in Newfoundland. And so we have those kind of vehicles for trying to sort of promote and protect, and also build some kind of a balance around people have to be able to work, but also let's protect some of this incredible geology. So there's those vehicles. I'm working with national parks through the Canadian Federation of Earth Sciences. Leslie Heimers, who's here with me today, she and I have been working with national parks. We had a pilot project this summer, which was a geologist in residence program at Pukasau National Park. And so a volunteer came for 2 weeks to Pukasau to look at the geological assets of the park and help them to interpret them to the public. So I think if we can start getting geologists back into those national parks, which were inscribed in most cases because of fabulous, spectacular landscapes that are underpinned by that geology, if we can start to tie the geology of those places to everything else that's fabulous about them, then we'll have another way to sort of protect interesting and spectacular geology. So it's starting to get some recognition, and certainly this day being designated is really helpful. So any other questions? I have no more questions from the floor. Oh, please.
So when we talk about biodiversity, we talk about its value to humans, and that it supports livelihoods and well-being and so on. I'm interested in we've got empirical data that shows that biodiverse areas generate more ecosystem services and so on. Has there been any effort to characterize geodiversity? And I know there's the mineral side of things, but even, for example, from a hazard protection perspective, what do we know about different landscapes and what that means for relative hazards to, so-called geophysical disasters and so on? So I don't know. There's a really good narrative about why biodiversity matters, yes, linked back to people. And I know there's an economic argument for extraction, but I'm interested in other ways in which that geodiversity connects back to people.
So I think there's some connections like hazards, as you and Tessa both were talking about. These really affect people's lives, right? Like landslides and earthquakes and volcanic eruptions, and these kind of things are very impactful in people's lives. And so we have a lot of work done in those sectors to try and categorize the risk, categorize how we can respond to it, how we can modify buildings and that kind of thing so that they can withstand different things. So we have certain areas of geodiversity, I guess, that we work really hard at trying to think about, because they really do resonate with the public, right? But I don't think it's universal at all. Well,
I just want to add in that it really is, it's really bringing that public knowledge, like how earth science and geodiversity is really important for society in general. You talked about natural hazards, like like geohazards in general. We're also talking about energy, oil and gas reserves. Like we need this to survive. We talk about the mineral resources. We're talking about water resources. We're talking about food too. We haven't talked yet about soil science, right, and where can we farm. So it really is, it's a cornerstone to our society, and it's just being able to educate people on how important earth science is and geodiversity is for our society. So, and I really like your comment earlier about how we really need to bring that to elementary school and to high school, and that should be a stream of science that people, that students can start and get excited about. There's so many jobs in the geosciences right now, with people retiring, and they're exciting jobs. I mean, look at the pictures you showed. Like if you were to present that at a high school, I'm sure enrollment in university and geosciences would increase. It was phenomenal. Like your research is phenomenal. So it's just how do we bring that education to people at the elementary school level to get people excited and to really show them that earth science and geodiversity is so important to our society in general. So.
Thanks. We're working on it. We're doing that here tonight. Yeah. So are there any other questions out there in the dark? Please.
Is this on? Hello. I'd like to thank all the speakers for the talk. It's been fascinating. I think that we've been skirting around a whole series of knotty problems. There is a word, I believe, when knotty problems become entangled with other knotty problems. And I think that the idea of connection is vital. But until this time in history, it was all right for people to study their fields independently. But now everything is entangled. I'd like to know if the board is looking forward to the future with equanimity or with trepidation. Because, yeah, do you think that it will be possible to get to talk together?
Possible, yes, absolutely. But, you know, like we were talking about, is there a geopolitical conversation about making sure everybody across the planet has what they need? These are problems that may not be solved by scientists or educators, but you know, if we're in the room with those people who are making those geopolitical decisions, municipal planning decisions, then perhaps we have a chance to, you know, make those connections and move things forward and solve some problems together.
I mean, we have to. We are at an absolute critical time in the development of the natural world and the destruction of the natural world. So the information has to keep on coming. Solutions have to be found, and you know, people have to come up with new ideas and work together. I mean, we just have gone through, you know, the destruction in the Maritimes. You know, we all saw those images. You know what happened there with the intensification of storms. And I mean, that's only one example. You know, I mean, there are so many more, and we cannot stay idle. We cannot stay idle. There is no choice here anymore. We were too complacent and it is really, I often think about this. It has been my generation who, like my father, he's not anymore there, but my father was the biggest environmentalist I knew. He came through the war generation, and of course it was very hard times, and he never wasted one single thing. And he kept that through all his life till 92 when he passed. Now it is our generation which really, you know, like lived this grand style life. And I feel terrible guilty for this. And I'm thinking often, what could we have done to go in a different direction? And now we know with the young people coming up, they want to do it differently. However, they don't always have the facts. They have a lot of enthusiasm to make change, which I applaud for, you know, totally. However, they also need the facts, because we cannot always jump, you know, immediately into a whole new system, and you know, it doesn't work. So they need that education, but they have to keep the enthusiasm. And we really have to give them room to shape this planet for themselves. They deserve that. They absolutely deserve that.
Thank you. I think that is a perfect place to end our evening together. Thank you to Claudia and our panelists, and for giving your time to help us explore this idea, this new idea of geodiversity, and why we should all care about it. I want to thank our sponsors, the National Research Council of Canada, Ingenium Foundation, the Canadian Geological Foundation for their support in making the evening's discussion available to everyone in Canada from coast to coast to coast. I would like to thank all the people behind the scenes, including Moira McGrath, who is here somewhere, who worked painstakingly for the past 6 months or so to make this happen, and thank you very much. And to the lovely technicians behind the scenes, they're back there behind that glass, who made sure we could all be heard. And finally, thank you to our wonderful audience for joining us and celebrating both in person and virtually, and for your thoughtful and engaging questions to our discussion. For those of you here in person, you can meet us and meet the presenters for a networking reception before you head for home. On behalf of Carleton Faculty of Science, the Department of Earth Sciences, Ingenium, and the Canada Science and Technology Museum and Curiosity on Stage, we thank you again for attending this evening and wish you safe travels home.